Okay, physicists, welcome to our once a week meeting of physics. Since we didn't have class all week, I have not talked about last week's quiz. Last week's quiz was, our scores were a little bit low, so I want to go over some of the issues that we had in this. So, where are we in our unit? We've done chapter 5 and 6. Now in the next week and a half, we're going to do 7 and 8. And then not this coming Friday, but the week after that, we're going to take our Unit 2 test. Okay, so what we've done so far, we've basically done Newton's laws. And where we're going is that we're going to do energy. So our most important Newton's law is, of course, F equals ma. Whoops. My machine only recognizes the pen that I have if it's been opened while the sketch pad I have is plugged into my computer. Okay, so yeah, the most important is F equals ma. That's your Newton's second law. F net, remember we add up all the forces and they cause the acceleration. It's a vector, so it works in every direction. Our forces are in newtons, which is kilograms, meters over second squared. And if an object pushes on another object, or if an object rather is pushed on by another object, it also pushes back on that object. So this is the second law, this is the third law, and the first law just tells us that we don't need to explain motion, we need to explain acceleration. So if there's a change in motion, that's what we need to explain. Okay, so we've done a lot of practice on that. What was our most missed Newton's third law question was this one. And the thing that was a little bit confusing was that some people thought that a force on an object produces another equal in magnitude but oppositely directed force on the object. Now I realize that's a little bit ambiguous, but the better answer is that it's on another object. So if there's a force on our object 1, that is counteracted by a force back on a different object. So the thing to notice, for instance, is that even if an object is just sitting on the floor and the normal force and the gravitational force are on that object and they have the same size, they're in opposite direction, these are not third law pair. In fact, what is the third law pair? Well, there's a force being pushed down on the surface. That's by the object. That's the weight that it feels. And there's also a gravitational force that the object is putting on the Earth. So these both do have Newton's law pairs, where there's a force on the surface on the object on the surface on the object, and then the gravitational force of the object on the Earth, the gravitational force of the Earth on the object on the Earth on the object. But they are not on the same object. The paired forces have to be on different objects. Okay, so since we don't have a quiz today, I thought maybe it would be good just to do a review problem on each one of these topics. So here's topic 1. We've got a team of dogs pulling a sled with a mass of 2m, and they're pulling with a force of P. A second sled of mass m so it's a less massive object, is attached by a rope and pulled on behind the sled. The tension in the cord is T, assuming frictional forces are too small to consider. Okay, so we're not doing, that's chapter 6 stuff. We're only doing chapter 5 stuff here. Determine the ratio of the magnitudes of the forces P and T. That is, find P over T. Okay, so as I've indicated here, this is going to be an F equals ma type of problem, but let's try to think, how are we going to set this up? Well, we've got two objects. Each of them has to follow Newton's second law, F equals ma. So let's go ahead and let's draw the let's draw the forces on them. So we don't have to care about friction. What do we have to care about? Well, we have a normal force and we have a gravitational force. That's not really going to be that important in this problem because what we care more about is this pulling force pulling forward and this tension force pulling backwards. On the other hand, this other little mass, what forces are acting on it? Well, it's going to have a smaller force of gravity because it's less massive. Remember, the force of gravity is just m times g. That's 9.8 on Earth. And then Fn would be smaller as well. And then it's getting pulled forward with T. And it tells us that we're going over ice, so we don't need to care about friction in this problem. And that's it. So what I could do is I could write out, this is a mass of m, this is a mass of 2n. I can write out F net equals ma for each one of these objects in the x direction. Okay, let's do it. Ma equals T. Okay, T is the only object pulling on it in the x direction. Okay, let's do it again for this one. Now, the thing to realize is that in principle, these two objects could have different accelerations, but because they're all nicely pulled along by that dog sled team, they're going to have the same acceleration. So let's use that. We can say that 2a equals, and then we have to, so ma equals, let's put the net force. What are the forces acting on this object? Well, P is going to be pulling forward, and then T is going to be pulling backwards. So minus T. Okay, well, here I have an expression for T. How about for P? Well, if I have that 2a equals P minus, let me put in ma for T there. Ma, let's add ma to both sides. 3a equals P. And now I have 3a equals P, ma equals T. So if I wanted to find P over T, it would be 3a, this should be 2m times a, and this should be 3m times a. So P would be 3ma, and T would just be ma, so that equals 3. Okay, so there's a couple of tricks in here, but the clear idea is draw a free body diagram, write down Newton's second law, and then see where you're at and try to see if you can get an answer for what they've asked. Okay, so that was chapter 5 stuff. Chapter 6 stuff is about frictional and centripetal forces. And the idea for the frictional forces stuff is that the normal force and the frictional force are linked through some proportionality constant called the coefficient of friction. And so we have two equations for it. You typically have a coefficient of static friction, which is bigger than the coefficient of kinetic friction. And in the case of the equation for the coefficient of static friction, that gives you the maximum possible frictional force. And so it could be anywhere in this range, depending on how hard you're pulling on the object and it's not moving. And then once it breaks free, you get an approximately constant amount of friction that's just based on how hard is the surface pushing back up on the object. And in chapter 6, we also talked about centripetal forces, where the force is always towards the center of the circle, and that's not a separate force. It's not a separate force like friction or tension or gravitational force. It is just whatever net force happens to be acting on your object to keep it pushed towards the center of the circle. And as we learned earlier, in I think chapter 4, the acceleration of an object towards the center of a circle is based on its speed and its radius. And then what we did was we just said if F equals ma, then we have some amount of force that you need to be pushing an object of mass m to keep it on that trajectory. So this was quite a tricky problem. I will have to acknowledge that. But it says a brick is resting on the surface of a flat board. As one end of the board is slowly raised, what changes, if any, are there in the normal and the frictional forces exerted on the block? Well, the key point to realize here is to use this diagram. So in this case, if this brick is just sitting here, there's some normal force and some frictional force that are keeping it in place, because otherwise the gravitational force would pull it down the surface. So there's your force of gravity. Now notice what's happening as this angle gets bigger. As this angle gets bigger, so that theta here is proportional, is actually equal to this theta there. We proved that. And what's happening is that when the board is totally flat, that's where you get your maximum normal force. So Fn, as this slope is getting steeper, Fn is getting smaller. Okay, and you can see that because your cosine of theta looks like this. So it's getting smaller as your angle, that's your cosine of theta. And your sine of theta looks like that. So your F friction, at least until you, for a while, is getting bigger. Okay, so that's our answer there. So, okay, let's try another problem. This one's a little tricky. I wouldn't have given this to you as a quiz problem, but it's a good one to think about. Okay, now everyone has seen probably the magician's trick where you've got a table full of dishes and a tablecloth, and you whip the tablecloth out and all the dishes stay there. Now, presumably, if the tablecloth was made of sandpaper and the dishes had a very rough bottom, you couldn't do that. So there's got to be some coefficient of friction that would stop those objects from just staying there. And that's what this problem is about. So it says if we have a crate of mass m is on top of a frictionless surface. Okay, so that's box mass m. Now what we're doing is we're putting another crate on top of it. So there's no friction between this bottom surface and this block. There is friction between this block and the block on top of it, which also has mass m. It says, assuming a horizontal force F is applied to the bottom crate. So we're going to put a force right there. Determine an expression for the minimum static coefficient of friction so that the top crate does not slip. Okay. Well, what I would do at this point is draw a free body diagram for the top block and for the bottom block. Okay? So, what are the forces acting on the bottom block? Well, there's the force of gravity, so that's little m times g. There's also the force pushing down in this direction from this, and that's also going to have a little m times g force. So, just to put this clearly, this is pushing down, so that it's because, I mean, a better way, I suppose, to do this would be that this is if I call this object 1 and this one 2, this box is pushing up on that with a normal force, and let's call that the normal force on 2, and it has to have a Newton's law paired force F normal 2 pushing down. Okay, and then there has to be some big Fn pushing up, and that's the force of the normal force on this one. And then there's got to be a big this mg acting on this top block, which is just your force of gravity. Okay, now there's also, we said, a force pulling this forward. Let's call that just F. Now, here's the key. If this block is to move forward, it has to have a frictional force pulling it forward. Okay, but this force forward on the top block means there's a force backward on the bottom block. All right, so what are we doing here? Well, essentially, if you look at this situation, what's happening is that your Fn2 is just going to have a magnitude of mg. So this is mg. That means that your Fn1 has to have a magnitude of 2ng. Fn1 equals 2 times mg. Okay, now let's try to think. What is the force of friction that we're going to experience here? Well, the force of friction backwards in this case is not just a sec. Okay, sorry about that. So this is the normal force on the first object, but that's not really what's relevant. What's relevant to producing this frictional force is going to be the normal force. So I'm just going to erase this for space. What's relevant for producing this frictional force is the normal force on the second object. So that's just going to be equal to your mg because it's canceling that out. And so your force of friction in that case is going to be mu times mg. But I don't know what mu is. That's what I want to find out. Okay, so how am I going to figure this out? Well, let's write down our x direction F equals ma for each one of these. So ma equals just the force of friction in this case, which is going to be mu times m times g. Okay, now notice these both have the same mass, so my bottom object is also going to be ma, because I'm just using F equals ma. But what forces do I have acting on it? I have F in the positive direction minus okay, minus my force of friction. But it has to have the same sign, so it's going to be minus mu mg. Okay, so what am I going to do now? I'm going to put in this for that, and I get mu mg equals F minus mu mg. And then I'm going to bring this over, and I get 2 times this equals F. And now remember, what I'm looking for is an expression for the minimum static coefficient of friction. So I'm looking for that mu. And so I go ahead and find it as F over 2mg. Okay, so this is an example of a problem that's a little tricky, but again, it's following your Newton's laws. You draw a free body diagram, you use F equals ma, look where you are, and go ahead and solve. Now, another quiz question that had quite a bit of confusion was one that was on the centripetal force. And I thought I would go over this one quickly because I had an illuminating conversation with one of you over what the confusion on this problem was. So it says a steel ball is whirled at the end of a chain in a horizontal circle of radius r with a constant period t. If the radius of the circle is then reduced to size 0.25 r, okay, sorry, somebody's banging on the door here. All right, false alarm. Okay, if it's reduced to 0.75 r with the same time t, what happens to the centripetal acceleration of the ball? Well, if you have the acceleration here, and if you simply put in 0.75 in for r, you'll get 1.33. Now, why is that wrong? The reason that doesn't quite work is that your v also depends on r and t. So what you need to do in this problem is say a equals v squared over r, but your v also depends on r and t, so you would have to write 2 pi r over t squared over r, which equals 4 pi squared r squared over r, which is just r, over t. Okay? So if you keep t the same and you reduce r to 0.75 r, what happens to the acceleration? It just goes to 0.75 times its initial value. Okay, so that's the idea. Now, today we're going to go ahead and do a new unit. Not a new unit, but it's kind of the back half of this unit 2. So we've done all of these problems trying to figure out how they're going to move by adding up the forces using F equals ma. Now we're going to do these same problems in a sort of a different way. And the way we're going to do them is with energy. Okay, so we've talked in terms of forces. Now we're going to do a lot of the same problems, but sometimes they can be more elegantly stated in terms of energy. Now, what is energy? It's a little bit of an abstract thing. What you're doing is you're assigning a number that has something to do with something in the problem. And the reason why you're picking these numbers in that way is so that you can add them all up, and that total number where you've added all the energies up will stay the same. Okay, a little bit abstract. So let's not start on this really abstract level. By the way, the guy who developed a lot of this was named James Prescott Joule, who was a brewer. He made beer, and he was interested in how to most conveniently get heat out of objects. And so he developed the idea that heat and motion of particles were basically the same thing. They were connected because they were both types of energy. So that's why we named the unit of energy the joule. Now, the first type of energy I'm going to tell you about is the kinetic energy. And it's just a number. If you have an object of mass m moving at some speed v, if you take 1/2 m times v squared, we're going to call that the kinetic energy. What is kinetic energy? It's energy of motion. All right. Now, I would like for you to now pause this video and go ahead and watch a YouTube video, not because the YouTube video is going to teach you everything, but it will help these concepts to roll over your brain. You're going to hear the current terms for either the first time or a new time, and it'll be good for you. Okay, so pause this, go open up the PowerPoint that I put up, and watch yourself a YouTube video. I'm going to pause it.